Welcome. In the last lecture, we have discussed the smelting reduction. There is a two-stage smelting reduction process, mainly the Corex and the Finex process. And in this lecture, we will concentrate on the single-stage smelting reduction process. Mostly, there is a two processes are available. One is the Russian process, that is the Rommel process. Another is the Finex process. Okay. So, this is the material flow diagram in the Rommel process. You can see you can directly use the ore fines and the coal fines into the reactor, okay, and you push the oxygen, and this is the reactor. So, one reactor, in a single reactor you just dump everything, and this is not only the ore fines. In case of the Rommel, you can use any kind of waste material, iron bearing waste material. In a single stage reactors, basically any kind of in two stage has some restriction, but in the single stage you don't have any restriction. You can use any kind of iron bearing waste material. That's why this process, basically single stage smelting reduction process, cropped up because of utilizing of the iron bearing waste material from the plant. Okay, so that's why it is not only the iron ore fines. It is not the ore fines, it can be any kind of waste material, iron bearing waste material, and the coal fines that is charged into it, and you can charge the oxygen, and then you generate intense heat, take everything into the slag phase, and then the carbon will reduce the iron oxide from the slag phase to iron, and by gravity iron will settle at the bottom and the reaction will go on. But only problem in this process, a lot of carbon consumption, that is your coal consumption is quite high, because you are doing everything in a single process, and so it is not that effective, and so rich gas come out, and then you have to use this. There is a steam turbine is there, that is to generate the power. Okay. So this is the simple process. I will talk about that thing, and this is the details of Rommel reactor. You can see it is a greater view is there. So basically you can see oxygen is injected from here as well as from the bottom. This oxygen is there only basically to directly for combustion of the carbon to generate the heat. So you can combustion of the carbon and generate the heat, and the carbon is there, and also gasify the carbon also to CO. And this oxygen, upper oxygen, basically for the post combustion of the CO that is evolved from this process. So that also generates lots of heat, and you can have to have the post combustion such that your coal rate decrease to some extent. Okay. And so secondary oxygen and primary oxygen are there, and you can see that is a active bath is there above the slag, because you are giving the oxygen and then it will generate the CO. So it will generate some kind of emulsion above the slag bath, and where the reaction will be much faster. So this will be a faster process, and that is called the active bath. Active bath is there, and below that there is a slag, and then finally it is the iron layer. And that you can see this is the iron comes out from here, and the slag from the top. You can take out the slag from here, and this is the details. Charge coming from the top like this, and flue gas is coming out like this. Okay. So features is a single stage process. As I said, it is a single stage process. Steel plant waste like mill scale that is generated in the hot strip mill. So that mill scale, and the blast furnace LD dust, from the blast furnace dust, LD dust, those are very iron bearing dust. Dry sludge from the gas cleaning plants. You have a dry sludge from the gas cleaning plant, you will also have sludge, and that sludge obviously contain a lot of iron bearing irons. And the iron bearing non-ferrous melter slag, oily steel turnings, that also can be used up. Okay. Non-coking coal usually up to 20 millimeter size, not bigger than that, it is favored. That is up to 20 millimeter size you can use, because then the burning efficiency become higher, and with moisture less than 10%, because higher the moisture, your burning efficiency and the flowability of the coal also become less. And the volatile matter less than 20% is preferred, but high volatile coal can also be used, because volatile is good, basically it increases the combustibility of the coal. But if your volatile is much more, then obviously your fixed carbon in the coal will decrease. and that will, as a result, heat generation and the reduction will be less. Okay. Small scale production, basically in this scale, that is the 2 lakhs to 1 million ton per annum. Hot metal is possible along with the flexibility of operation. Excellent metal quality, that is the 4% carbon. You can see there is a silicon, manganese, sulfur are quite less, and temperature of that around 415. And here in the single stage reactor, one thing is that the slag that is generated, okay. So here basically you can find the emulsion forms in the upper part of that thing, and there some slag metal partitioning take place because slag contains AFO. So, and then AFO basically takes up some, then oxidizing, it is oxidizing, the slag is become little oxidizing there, and then they can partition some amount of the phosphorus and sulfur. So, that is why you can get a very low phosphorus also. You can see Romil hot metal contains 60% of input phosphorus, okay, and 40% go off. How? Now 30% phosphorus is partitioned into the slag, it goes into the slag, and 10% can move with the exit gas. So, around 60% of the ore phosphorus reports to the hot metal, 40% go off. That is the advantage, because the slag in the emulsion, some kind of emulsion form, and there some partitioning, efficient partitioning take place in presence of the AFO in the slag. That is the major drawbacks, that is the coal and oxygen consumption are quite high, because you are doing everything into the single reactor, and also you are producing a very high quality hot metal with less phosphorus, less sulfur compared to the blast furnace, compared to other SR process. But you are doing everything in a single reactor. As a result, your coal and oxygen consumption is high, typically 1500 to 2000 kg per ton of hot metal. That is the coal consumption. It is that the coal consumption is around 1502 compared to the blast furnace maximum 500. In the Corex also maybe maximum 1000 kg of coal per ton of hot metal. Compared to these, it is 2000. That means it is around twice that of the Corex. So that is the major bottleneck, and the gas that is coming out is very rich. So in that case, you have a load on the off gas. Okay. It is a Russian technology. The first pilot plant was put up at Novolipetsk Iron and Steel Works NLMK in Russia in 1985. A commercial plant is also erected at Myanmar, 2.5 million ton capacity, to treat their very low grade iron ore. But but still now today, I do not think there is not much of success today of this Romil process. Okay. So now I am coming to another single stage process, that is called the His-Melt process. What is that? In this case, His-Melt process. In His-Melt process, the unique thing you can find that most of the SR process uses pure oxygen and room temperature, and His-Melt process uses hot blast, that is the preheated air blast, oxygen enriched air blast. Okay, preheated oxygen enriched air blast. So they use the air blast, and this oxygen is charged from the top, just like in the oxygen lens, through a top oxygen lens, just like in the BOF process, the basic oxygen furnace that we use. So similar type of this thing, but here you use hot blast. Okay, it's hot air blast, oxygen enriched, obviously it is enriched with the oxygen, but hot air blast compared to pure oxygen in all SR process at room temperature. So what is the advantage? First advantage is that if you use the hot blast preheated at 1200 degrees centigrade, and here you are considering, so there is a lot of nitrogen, so you are giving lot of sensible heat with the hot air blast. So you are giving lot of sensible heat, and because of that you can reduce the coal rate, that is the energy required from the coal you supplement by the sensible heat of the hot air blast. So your coal rate will be reduced. So that is the idea. Second thing, but you have to preheat it to 1200 degrees centigrade. So you have to have some mechanism for preheating the air blast. Okay, so that is there. And then this is the oxygen, it comes in the form of hot air blast. and coal is there. Coal after dryer, you can directly inject into the liquid bulb. So, this is the coal powder is not dumped on the top, it is injected. It is injected inside the liquid such that the efficiency of coal burning and reduction become much more efficient. Okay. Similarly, you can see the iron ore fines, this is also dried, and after dry it, hot ore at 680 degrees centigrade, basically it comes and then it is also injected. It is also injected. Okay. So, and this preheating is basically done by taking a part of the off gas here for preheating, okay, and rest of the off gas goes to the power plant. So, off gas from the smelter gasifier, that is the only unit, that is the unit, it basically goes to, a part of it uses for preheating your rear, that is the iron ore, and rest of them go to the power plant. 20 megawatt power plant is there. Okay. And then so, this is the process. So, here you can see directly use the iron ore fines, coal fines, but injected, it is injected directly into the hot metal. This is the very unique feature, injection features, that it can increase the efficiency of melting and utilization of the carbon and iron ore become much more efficient utilization. Okay. And second thing is that you are using the hot air blast that carries lot of sensible heat, and that can also reduce the coal rate. So, coal rate will decrease from two counts. One thing is that because of preheated air blast. Second is that since you are injecting it, the process efficiency become much more faster. Melting of the iron ore become faster, and then coal gasification and the coal oxidation also become faster. Okay. So, that basically process become efficient, your coal also decreases. Also the preheat air blast, that is also coal decreases. And also you do not have to use a large amount of oxygen is not required. So, only oxygen plant, it will only be enrichment purpose. So, this is an overview, you can see that is the in a very nice picture it is there, so melting reduction, you can see coal and flux also, that is injected in this here, iron ore also injection like this, just like you are injecting, and then slag is coming one hole and metal is coming through here, and the hot air blast coming from the top lens and off gas is coming out. Features of the HISMELT process, first is that it is a single stage process. Okay. So, as I said, that is the method of solid injection using high speed lens ensures that the capture efficiency in the melt is high, and even ultra fines can be used directly. So, ultra fines you can use directly. So, usually the fines melting is the problem. If you dump it, it will never melt very efficiently. You have to, that is why the Phoenix process, they basically break it and put into the hot metal, liquid iron. In this case, you are injecting it. If you inject it, you can directly inject the very fines, ultra fines also you can inject it, and then they will, melting will be much faster. Okay. So, as I said, instead of pure oxygen, there is the oxygen enriched hot air blast is using a top lens that gives a lot of sensible heat. Utilization of the export gas not as critical as in many cases like raw melt and the Corix process, because the coal rate is much less here, coal rate is much less. Okay. The 5 to 6% FU level in the slag here also, in all single stage process, FU is there in the slag, and that FU you can utilize to partition some of the impurities. Okay. Strong partitioning of the phosphorus slag metal, typically around 80 to 90% phosphorus goes to the slag. So, it is a much better process that way. So, 80 to 90% phosphorus goes to the slag. In the raw melt around 60%, 40% is partitioned to the gas and slag. Here 80 to 90% phosphorus is partitioned into the slag. So, only 20% of the ore phosphorus reports to the hot metal. Okay. And then pre-reduction of iron oxide, you are doing some pre-reduction and the preheating, and top lensing of oxygen enriched air blast provides substantial productivity enhancement. As I said, if you top lens it, then also you generate some lot of emulsion formation, because when you lens it, then the FeO and the carbon reacts, the emulsification takes place just like into your basic oxygen furnace, LD furnace. So, emulsification when it is done, then the kinetics become much faster. So, this is the thing, process can use 50% high phosphorus iron ore and 50% plant waste like mill scale, BF does, BF sludge, etc. Hot metal produced contain 4.3 plus minus 0.15% carbon, and the phosphorus silicon levels are extremely low. That is great, 0.05 phosphorus, 0.05 silicon. So, it is almost like a steel, only carbon has to be eliminated. From this hot metal, if you take out the carbon, then it is steel is made. So, you do not have any load on the phosphorus and silicon for the steel making, very few loads. Small amount of phosphorus and silicon has to be removed during the steel making process, only carbon has to be removed. Okay. So this is process hot metal quality is much superior than the blast furnace also. Okay. So this is the Hismelt process. Now I come to another most Hisarna process. It is basically Hisarna plus Hismelt. It has some features of the Hismelt, basically the smelting reduction vessel. It is similar to the Hismelt process. And Hisarna iron, you can have a cyclone over here, and that basically used up to melt the iron ore feed and partially reduce it also. It is developed by Tata Steel Europe and the Rio Tinto, and you can see the ore. This is the reactor. You can see there is the neck. In this neck you have a cyclone here, and here basically similar to the smelting reduction vessel of the Hismelt process. You can see coal is injected and the oxygen is charging and the slag is there. Only the iron feed is not given into the smelting reduction vessel. There's the iron ore feed directly comes into the cyclone. So iron ore fines is charged into the cyclone, and in the hot atmosphere of the cyclone, the iron ore melts and partially reduced also. And since it is a cyclone, that is the iron ore basically on the surface, they remains on the surface of the snake, and then that trickles down to the smelting reduction vessel, and finally the rest of the reduction take place in the smelting reduction unit. So CCAV is basically the cyclone converter furnace. The fine ore gets partially reduced and molten and falls through the wall to the SRV. SRV is smelting reduction vessel. So iron ore fines are injected in the CCAV. As I say, it is not into the SRV. It instantaneously melts and partially reduced iron ore fines and trickles through the walls of the CCAV to the SRV for further reduction. So, and the rest of the reduction take place into liquid state into the SRV. And then the metal basically, here is the slag and the metal is collected at the bottom, and then you can tap it out. So here it is the CapEx, capital investment, and the operating expenditure. Also both the expenditure, capital and operating expenditure, are lower compared to the blast furnace. Wider range of raw material you can use much wider range, alkali raw material, and then zinc containing raw material, iron bearing ore you can use, phosphorus, tin, sulfur bearing iron ore you can use. Okay, so that is the advantage. And iron bearing solid waste, because iron bearing because this wide range of raw material is used, because zinc is not a problem, it will vaporize and go away from the system, because you don't have in blast furnace all this problem comes because it chokes the shaft, because the zinc vapor choke the shaft, and if presence of alkali, the raw material swell and then crumbles, generates the fines, choke the shaft. So all these problems are there. Okay. But in this case, because of this raw material, this constituents are there in the iron ore bearing ore also, then also they can be vaporized and go away from the system. Absolutely no problem, because here there is no shaft furnace, so no problem of shaft furnace related problems are not there. So any kind of ore you can use it, and iron bearing solid waste from the plant you can use, and 20% lower energy usage and CO2 emission per ton. And one thing is that in the Hisarna process, major thing is that from the off gas, the CO2 is sequestered. So the CO2 sequestration is in place, and that is the CCS technology by which you can convert it and store. and it has been, the plant has pilot plant demonstration has been there with continuous 6-month production has been there, but still it is not in the commercialized stage. Commercialized is yet to be established, but pilot plant continuous 6-month operation has been tested. So this is also a very future smelting reduction process which has a very bright scope of in future. Okay, so these are the reference. So in conclusion, so what you see, there is the Acer process. Acer process basically developed to avoid the problems of DR process like accretion formation and then your sticking of the pellets of this thing, and also to avoid the, finally it can be compared with the blast furnace also, because the product of Acer process and the blast furnace both are the hot metal almost similar quality, and sometimes Acer hot metal is better than that of the blast furnace. So only difference between the two processes is that in the Acer process you can use very low grade raw material like the coal, non-coking coal, and the low grade iron ore fines. So any kind of ore fines, ultra ore fines, and then you can utilize, that is the iron bearing solid waste from the plant. So all these things, low grade raw material you can use into the Acer vessel, but you can get a similar quality of hot metal that of blast furnace. Only thing is that in this, because the reactor is designed in such a way such that it does not have much complexity that of the blast furnace. But the advantage, but the major disadvantage of the Acer process is that unless you utilize the off gas effectively, the process will never be beneficial. Okay, so off gas utilization is a must. Okay, so you have to generate the power that will sustain this process, as well as you have to sell this power outside such that the process become much more effective. And this process are basically two-stage process, because Acer process initially it was conceived it can be single stage, or Acer process can be two-stage process. Okay, and two-stage process you can utilize the gas little more effectively. Okay, that's why the two-stage process, some process efficiency become little higher, but single-stage process are also come out to be very fine, for especially the Hismel process which is commercialized also, and this off gas credit is also less, and the hot metal quality is excellent, and you can use any kind of raw material in the Hismel process. But most popularized process are the Corex process and as well as the Phoenix process. Corex process is most popular, and it is basically a two-stage process, because if you want to use a ore, iron ore, then I think lumpy ore or the pellets, then the two-stage process is better. Or if I want to directly use the iron bearing waste, iron ore fines and all this thing, then single stage process can go. Okay, so these are the things, because we have in India, we have the iron ore deposits are there. So we have the availability of the lumpy ore, little low grade alkali iron ore lumpy ores are available are there. So in that case we can go for, that is the Corex process, that's why it has come, Corex process has come. The Phoenix processes can be used for treating a very low grade ore, and also your that is the waste from the steel plant and all these things. Okay, so all this process has a very potential to in future to grow, and in India also we have Corex process, and in future hopefully we will get Hismel type of process. Okay, thank you very much.